Okay, so the second talk is about the machine proofs for certain interesting Adams differentials. So basically, we got a lot of interesting Adams differentials, and so that in the end, if you go to 126, that there are very few dots left. This dot cannot be theta 4 square, and yeah, so there's only one dot here. And I want to make one comment that the computer program knows more than the plot. So for example, the plot says that it does not know whether this D4 is 0 or not. But actually, keep in mind that what we prove in the computer data is a lot of contradictions. So sometimes, if there are 4 candidates and you get 2 contradictions, you cannot get the differential, but the computer is aware of that there are only 2 options left. So for example, for this differential, there are 2 options left. We can read that from the machine generated proof that the differential should be either the sum of these 2 dots or the sum of the 3 dots. So the complexity comes from the fact there's a parallel D4 alongside the unknown D4. So it makes the ambiguity, but we are 100% sure that this D4 is non-trivial, and it's going to reduce the dimension of this degree by 1. So in the end, there will be actually 1 dot left, and that 1 dot will be detected by TMF. So it cannot be killed by H6 square. There's only 1 element we need to rule out for the last Kervaire invariant one problem. So yeah, so in this talk, my job is to tell you some interesting machine proofs for Adams differentials. Okay, so I have to make one comment on the software I'm using for this machine proofs table, the table of machine proofs. I recommend some software called DB Browser for SQLite. So my machine proof contains 22 million lines. So as far as I know, the Microsoft Excel can only open a table up to 1 million lines. So in my Zenodo repo, I also uploaded a set of 22 spreadsheets so that you can open it in Microsoft Excel. But there are 22 of them. It's not easy to use. So I recommend this software. After you install this software, you can just double click the database and you can pull out the whole table. And you can also, sorry, I should use the other one. Not this one. Okay, so you can also run commands. So basically all these commands are commands for getting data from the table. You are filtering the table out, and then the table, the software will give you the set of rows that satisfy the condition you tell the program. So in this language, it's very easy to learn. It's a language called SQL. You can Google search it, but it's something very simple. You just say, let's select star from the table log where something and something and that's it. And after you run the command, you give you the subsets of the whole table, which is like 22 million lines, and the program runs very fast. That's why I recommend this for reading tables. Okay, now let's go ahead and I will show you the machine proofs for. Okay, let me describe what data I have first. So our proof for the last Kervaire invariant one problem depends on the machine calculation. So you can find all this on the website. So the program starts with the following data. We have Adams E2 pages. We have map between E2 pages. We have D2 differentials for some CW spectral up to some range. And we have 3 manually added differentials. The first 2 comes from the image of J. So these are in very, very high stems. So I can show you the plots. So these are are in these long towers. So in 127, there's a very, very long tower of H7. So because it's a very high stem, the computer is having difficulty for deducing this. But we as a mathematician, we know that this for sure because we know very well about what the image of J is. So I just go ahead and add in these two differentials, one in 63 and one in 127. And then I also add a third differential, and that's a third differential in TMF. And this can be deduced by power operations by Brunner and Rognitz. So I can show. So it's the D3 differential right in the middle. So by the way, let's tell you a feature of the plots that you can add a question mark and write data that equal TMF. Then sorry, it's not this web page. TMF, and you get plots for TMF. And okay, that's the D3 differential. Somehow the computer cannot find any contradiction, assuming that this D3 is 0. So, but we do need this D3 differential to get to the results for the last Kervaire invariant problem. So I just go ahead and add this D3, and that's it. That's all the differential I manually added in. The proofs of them are very solid. This is by power operation. Okay, and all the rest are automatic. And we also have a non-public version based on differentials known in the literature. We just manually add in something that the computer doesn't know yet, but in literature it's known. Then, but it's non-public. So the publication, because we are not 100% sure that everything is correct, so we only make the one almost automatic public. Okay, now let me give you some examples of machine proofs. So the first one is the very first non-trivial differential the machine produces. You can find this in the demo, in a very baby demo that I provided on the website. Then let's pull out the table. Okay, so actually you can find out that there's a line called out CSI. It means also here, it means that in the spectral cofiber of 2 and stem 25 and 10, somehow for degree reason, it's a boundary, it's an Adams boundary, and the cofiber sequence is irrelevant. So there's a CS here, stand for cofiber sequence. So it's kicked out from the cofiber sequence. It means that it's an Adams it's an Adams it's an Adams boundary. And let me show you this element. It's this element. So you can inspect the initial data of the plots. You can find out that in the cofiber sequence from sphere into the bottom cell of C2 and then to the top cell and then go back by boundary maps, you can find out that these elements.
Did we lose the screen sharing? Did we lose the screen sharing?
I
can still see it.
Okay,
but is anyone else having problems?
Yeah.
I'm seeing cofiber too. It looks like
that's
good
fine.
on my side.
Okay, fine. Okay, that's fine. So you will find out. So if you go to, let's copy this and let's write it's the cofiber sequence here. So yeah, let me tell you a little bit on how to read these plots. So this is a cofiber sequence. So you'll see strips of 3 columns. It corresponds to a cycle in the long exact sequence. So for example, these 3 columns, and you should read the plot from right to left. So the map goes from right to left. So this goes from pi 14 of, so let's assume that this is a cofiber sequence from X to Y and to Z. Then the right column will correspond to pi 14 of Z, and then goes to pi 14 of Y, and then goes to pi 13 of X. Then the next one is the connecting homomorphism, and then it goes on. So that's why it's in groups of 3 columns. And now if you consider, so for example, this is a Gaussian extension. you see that there are a lot of differentials of length greater than 1. It means that they are hidden, they are encoding hidden extensions. And because it's exact sequence, so this spectral sequence converges to 0. And I really like spectral sequences that are non-trivial and converges to 0. It's very useful. And just by this spectral sequence, if you inspect the data here, you quickly find out that this permanent cycle does not extend to any element, and it also cannot receive any hidden extension to it. And so by exactness, it should be 0 it should be a 0 permanent cycle. And now let's see that there are 2 possibilities to kill these elements. And this one is a permanent cycle. That's just by Leibniz rule. And so there's only 1 chance. So that's how you just get the very first non-trivial D3 differential out of kind of nowhere. It's just because for degree reason, you just consider the cofiber sequence. And yeah, and that's it. That's the very first proof of the very first D3 differential. Now let me tell you how to get the second, the very first D3 differential in the sphere. So that's okay. That's this D3. We have talked about it yesterday. And how to get this? And if you pull out the machine proof, and you go to, so you can search for this stem and for spectra that contains S0, and then you get these two rows. And there's one row that's assumption. The reason is T, that stands for try. And then you get a proof for why the D3 cannot be 0. So we are assuming that D3 is 0 here, and the proof is on the right-hand side. So, and you see that this proof a little bit weird. That it indicates that somehow you already know a D3 differential in stem 93, and you get use Leibniz rule, and somehow there is a D3 differential already in stem 107, and you get a contradiction. And I can explain why this very first proof, the very first proof for the sphere D3 differential is weird, because in the very beginning, the D3 differentials are wildly open. There are tons of uncomputed D3 differential. And our very first non-trivial differential is obtained in cofiber of 2. And this is how my machine works. The machine would try to compute D3 differential in a sphere first, and you cannot get the very first D3 differential. Then you try C2 next, and you get a D3 differential. And then you try C eta and C nu and C sigma in this order. This is like an artificial order of modules. You just try one by one. So because our very first D3 differential is in cofiber of 2, then next it's trying C eta and goes on. And by the time when we get back to the very beginning sphere, we already have deduced a lot of D3 differentials in many in the rest of our modules. And when you get back to S0, you already have kind of a lot of D3 differential in high stem. And why we have D3 in sphere? Because we have maps. If you have D3 differential in other modules, there's a chance you map non-trivially to D3 to the sphere. So that's how you get this proof. And you may ask, is there a way to tell the computer that it should prove the EG differentials by an EG statement? Yes, there's a way to do that. So in the very early stage, when you deduce the differentials, you can limit the computer, the program's access to high stem data and also complicated CW spectra, so that the very first differentials the computer obtain are just derived from some low stem relations and some simple CW complexes. So in that way, so there are certain commands to do that, and I've already done some experiments. So the point is that you have tons of proof for the same differential, because the stable homotopy category is kind of very rigid. You have many different proofs for the same differential, and so if you just run the command in the very beginning, you just choose a very random proof. So that explains this. But in the later stage, things get normal because we are after we have computed a lot, the machine seems to be on page with human on what's difficult and what's easy, and then they realize that if a differential it's hard in the literature, it's also kind of hard for the computer, as you will see from other examples. Okay, now let's consider the D3 on the. Let me see how much time left. I have 30 minutes. So let's see a D3 differential in stem 30. So that's here. That's happening here. Okay. So if you read the table, there's only one contradiction to rule out to get that you have to prove that this D3 is, if this D3 is 0, then you get a contradiction. And here is a proof. And you see that the proof is applying Leibniz rule to D0 in stem 14,4. And okay, so if you read this proof, you'll realize that from the plots, somehow the computer already have the D3 differential here in stem 44, and then it's pulling it back by D0. And then you can keep going on and figure out how the computer managed to prove the D3 in higher stem, like 44. Then let me go ahead and trace this. And it turns out that if you search for it in the table, it turns out it comes from nationality. First you get a D3 differential in a cofiber of 2, and it's done by proof by contradiction. The proof is here. Okay, so basically it's applying the Leibniz rule again. Remember that. So if you keep tracing this, you get back to the very first D3 differential we proved for C2. Okay, let's move on to the next example. So this is an interesting example. That's for stem 38 and filtration 2. That's also a differential we talked about yesterday. So it's this differential. So at this stage, the computer is not using synthetic general Leibniz rule yet. So the proof you see from computer is just by nationality and Leibniz rule. So you see that the proof is, so this one is interesting. You apply the Leibniz rule in a 3-cell CW complex. So CW new eta means it's a 3-cell complex such that the middle cell attached to the bottom cell by nu and the top cell attached to the middle cell by eta, because nu and eta, the product of nu eta is 0, so you can form this 3-cell complex. And if you manage to find a contradiction in this, so you manage to find a D4. So in the very beginning, you have a D4 in this 3-cell complex, and you can pull back to S0. So in some sense, this corresponds to certain massive classical massive product trick, but because we laid out by considering more CW complexes, here we are kind of considering massive product starting with nu and eta. So that's a philosophy here. Instead of using massive product, we are getting a contradiction in the 3-cell complex. Okay, so that's the proof. And you can, as an exercise, you can keep going on and trace how the computer managed to prove the D3 differential in CW nu eta. Let's move on to the next example. And so this one is the D5 differential, and that's a very hard differential in literature. So I think by the work of Wozhen Wang Xu and Isaacson, they managed to prove the D5 differential using the C-motivic data. I mean the Adams-Novikov stuff, and you can compare with it using the cofiber method, and you can get this D5. But right now, my machine can also do this D5 just by by Leibniz rule and nationality only. And let's see what the proof is. And it turns out that, so if you see a reason called DI, if you see an I, it means that the machine is deducing the differential backwards. Yeah, so it means that somehow the machine knows that this differential should be hit by D5 first, and then it's try to list all candidates of sources of the differential. So that's called DI. And when there's a row start with a DI, it means that the bigrading refers to DX instead of X. So that's something to keep in mind. So so when this is start with an I, then the gradient means the gradient for dx. Okay, so let's see what. So we all already see that for degree reason, if we know this is an Adams boundary, then immediately we get this D5 differential because that's the only possibility to kill these dots. And let's find out how the computer managed to get this Adams boundary. And let's go ahead and see what's before this line. It will give you a clue on how you get this Adams boundary. And okay, I think I missed the tab here. So actually, it's also done by a cofiber sequence. I think it's a cofiber sequence of nu or sigma. I don't quite remember, but yeah, you just consider some cofiber sequence, and just for by some deduction, you just get a discrepancy in the hidden extensions, and the discrepancy should be hit by a shorter extension. It turns out that for degree reason, there's no shorter extension, so it should be a zero permanent cycle, and that's how you get this boundary. Okay, let's move on to some even more interesting example. That's a D9 differential. So my machine produced the first known non-trivial D9 differential, and I think that's actually the last unknown differential within 90 stem. It's this D9 differential. There's a D9 differential from 85 stem to 84. The length is 9. So you can expect that the machine must deduce this by proving that this must be hit by an Adams differential, and you see that this is a large chance. And okay, let's go ahead and read the proof. So the proof is that the D9 differential should not be trivial. Okay, that is trivial. So actually, let's look out why. Okay, it's here. So it turns out that the clue is inside this DC2H4. So it's the dual of cofiber of 2 and H4. So it's a 3-cell complex where the middle cell attached to the bottom cell by sigma square, and the top cell attached to the bottom cell by 2. So that's what this CW complex is. So it turns out that if you consider a CW complexes, a cofiber sequence of this. So there are 2 cofiber sequence for this DC2H4. It's a 3-cell complex. You can break it into a subcomplex and a quotient complex. And it turns out that you get a D9 differential in DC2H4 first, and then you can pull it back to the bottom cell S0. And you may wonder how you can get the D9 differential in the CW complex, in this 3-cell CW complex. And the answer is what I just told you, that that you can consider certain cofiber sequence involving this 3-cell complex, and it turns out that just by this hidden extensor argument, you can get an Adams boundary. And it turns out that there is only one uncomputed differential that can hit this target, and it's a D9 differential. And then you pull back to the bottom cell, and that's how you get a D9 differential from DC2 H4. Okay, the next example is about what we've told you yesterday. Now we have generalized Leibniz rule. So this is an example that you can search for rows with the reason called SYN. It stands for synthetic method, which is the generalized Leibniz rule, and it's telling you what map the general Leibniz rule is using, and also the k variable. So if you read our paper, in one of the conditions involving k, so the k here is telling you exactly which case of the theorem we are applying, and you may wonder what the Leibniz rule is, what this differential is derived from. So here you don't see that the previous line. You are giving this condition and you don't see the previous line between this. So you can run another command and grab the lines right above this line. And the line right above this line will tell you what the differential this one is based on using the generalized Leibniz rule. So there are also general Mahot trick in the proof. Okay, so now I'm going to give you a very interesting proof, and that's a D5 differential here. I think here there's a D5 differential in the 71 stem. So this differential is obtained by okay, it's here. So the proof is quite long. If you go above, you see a lot of depth greater than 1. So let me tell you what the picture, what the geometry of the proof looks like in the next slide. So you consider the D5, and there are two possibilities. One, the D5 happens. The other one, the D5 is 0. And you can read this proof that after you assume that the D5 is 0, then the computer can make a bunch of further deductions. It proves that if the D5 is 0, then the next differential is D7 for the very reason. This one also must be 0. If you assume that D7 is non-trivial, you get a proof, you get a contradiction. So the D7 is all 0, and further on you prove that D9 should also be 0, and then it becomes a permanent cycle. So after you get a permanent cycle, you can start to ask, what's the hidden extension from this if you consider a map? And it turns out that in the end, you consider this cofiber sequence. This is a 3-cell CW complex with a 2 bottom cell and a top cell attached to the 2 bottom cell by 2 and eta. So you consider a cofiber sequence of this, and you get 4 hidden extensions, 4 candidates of the hidden extension from these elements, and they all get contradictions. So you can read this. Every one of them get a contradiction. You can read the proofs. So this is the geometry. So geometry of the proof. You assume it's 0, and the computer can make deductions, prove by contradiction, and you prove that the next one is also 0. Eventually, get a permanent cycle. Then you ask what the contradiction, what the hidden extension is. There's an upper script F, means that this is a hidden extension. All the 4 possibilities give contradictions. So in the end, you get this D5 cycle. So you see that it can be a little bit complicated. Let me show you a proof that's complicated in another direction. It means that there are lots of contradictions. Let me tell you one. That's RP. That's the RP infinity. RP from 1 to 28. So it's the real projective space from cell 1 to cell 28. So this proof, this D2 differential has lots of possible targets. So it's very dense. So it's from stem 125 to stem 124. And there are 8 dots there. So there are 255 possibilities. And the computer is a little bit dumb. If you consider a Leibniz rule, usually the same Leibniz rule can cut the candidates by 1/2. But the machine is right now is a little bit dumb. It just go out and try all linear combinations. So it has tried 7 linear combinations. It has tried 253 linear combinations for the possible D2 differentials, and you get 253 contradictions. All the proofs are written in detail here. So after you prove, you negate 255 possibilities, you get the result. So the proof could be difficult in this way. So the current implementation of the program would try to deduce differential when there are less than 1,024 possibilities. So if there are like more than 2,000 possibilities, the computer will just give up and try the next one. And that's how it works currently. Okay. So last, I want to make an analogy to the Sudoku, and also by the comment of a good comment about the SAT problem. Yeah, that's also a very good analogy. So, so this is a Stuku. I think many people have played with this. So I think the blank space kind of stands for Adam differentials we want to put in, and all the constraints on the Stu game is like the general Leibniz rule, nationality, etc. All the structures we know that holds in the stable homotopy category. And then by considering more and more CW complexes, you are kind of expanding the game, and you get more and more structure and restrictions. And actually, so for this particular Stu2 game, there's only one solution to this. So in some sense, my computer program is just kind of trying to solve that. In the end, there's only one way to fill in this. So actually, for each, so you often need to prove by contradiction to finish the game. And I think that's a very good comparison. Okay, that's the end of the first half of the talk. Thank you.